One of the applications of derivatives is to find the minimum and maximum values of a function. Of course, we could do this just by looking at the graph of a function using a calculator or a software program which would help us visualize graphs. But we're going to take a calculus-based approach to find the minimum and the maximum of a function. So minimum value of a function is the smallest value of a function in its domain I shouldn't say in its domain, or I should simply say on an interval. And maximum value of the function is the largest value of a function on an interval. Now, the reason why I changed the phrasing here from the domain to on an interval is because if we look at a function in its domain, then there could be more than one minimum value. There could be more than one maximum value in the entire domain. So the plural for minimum values is minima, and the plural for maximum values is maxima. And minimum is the lowest a function could get, so it is an extreme. Maximum is the highest a function could get, that is also an extreme. So collectively they are called extreme values, or in a plural form we simply call them extrema. Now there are two types of minima and maxima that one can observe. The first one is called a local minima or maxima, and the other is called the global or absolute minima or maxima. Suppose I have a function of that sort, and let's say that is the domain. I'll go down there. And if you look at this function, it's bumpy, it's going up and down, up and down. And you can see that this is a maximum point that the function attains, but it is a maximum point on a small interval, which would be right here. So that would make this point a local maximum. Same argument applies here. We have a large value, but that particular value is the largest on that shaded interval. So the interval was right here on the x-axis, the interval was right there on the x-axis, so that would also be a local maximum. Now I have a third point here. So on that interval, this point is the highest. So that would correspond to a local maxima. But this maxima is the highest of the other two, or of all three. So this particular value is larger than that one and that one. So this is also the absolute maxima of the function. Now, the minima, that is a small value on an interval along the x-axis. That interval would be that part. So the value that I just sketched is the smallest value on the interval that I shaded, and that would become a local minimum. In a similar manner, if I looked at an interval to the right and left of that point, then that point would also be a local minimum. But the question here is, does it have a global or absolute minimum? It does not, even though the lowest value is right here for the function. We don't call it an absolute maxima, or absolute minima, because this is an endpoint. So we don't typically look for an endpoint and say, okay, that has to be the local minima or the maxima. In a similar way, we can't consider that also, because that point is also an endpoint. So if I called A, B, C, D, E, then in this picture, A, f of A, C, f of C, E, f of E are local maxima, and E, f of E is an absolute maximum, B, f of B, D, f of D are local minima. And the coordinate B is where the extreme value occurs in the domain of the function, and f of b is the value of the function, or the maximum, or the extreme value. I'll just say value of the function. So the x-coordinate is simply the point where the extrema occurs, and f of b or f of d, f of a, f of c, f of e, those are all the values of the extreme value that we observe. So here are a bunch of theorems that are useful in understanding how we could use calculus to find extreme values, in the sense we've got to find minimum and maximum values of a function. The first theorem is called the Extremaly Theorem. So suppose we have a continuous function on a closed interval closed in the sense I am including A and B. And let a minimum and maximum occur at some points C and D, then C, D must be in the interval or the open interval A, B. Might seem confusing, but what we're trying to say here is if we have a function, so that is A and that is B, and if we suggest that the function has a minimum and a maximum, if it attains a minimum or a maximum, which in this case there is a local minimum and local maximum, so that's the local minimum, local maximum. Then the C and D must be in the interval A, B. In other words, C and D falls in the interval between A and B. And you've got to keep in mind that we cannot include the endpoints. So, which is why I changed the interval, which was closed right here, including A and B, to an open interval over there, indicating that I'm not including the endpoints A and B in looking at the extreme values. Another important theorem here is Fermat's theorem. What does the theorem state? So if a function, should rather say has a minimum or maximum at x is equal to c, then f prime of c would be equal to 0. That is, the derivative of the function at x is equal to c is 0. Well, we all know the derivative is simply the slope of the tangent line at a given point. So I'm going to draw a tangent line here and there in green, and you can see exactly at C, right here, and D, the slope is 0. In other words, if I find the derivative of the function at those 2 points, C and D, the derivative will be equal to 0. So what we're saying is if we know that a function has a minimum or a maximum at x is equal to c, then f prime of c has to be 0. There is a caution here though, in the sense the converse is not true. That is, if f prime of c is equal to 0, then it doesn't imply that the function has a minimum or maximum at x is equal to c. That's what we mean by the converse. In other words, the reverse is not true. A good example would be a cubic function and I have x is equal to 0 over there, and I want to draw a tangent line, and if I drew it, it's going to be right there. And the slope of the tangent line at x is equal to 0 is 0, i.e. f prime of 0 equals 0. But look at the picture though. The derivative at x is equal to 0, which is the slope of the tangent line, is 0. But do we see a maximum there? No. Do we see a minimum there? No. It's actually flat. So we don't have a maximum or minimum. So you've got to be careful when we interpret Fermat's theorem. If we have a continuous function and we know that there is a maximum or minimum at a point C, then the derivative at that point has to be 0. But the converse is not true, in the sense that if I know that the derivative at a point is 0, it doesn't imply that there would be a max or min. A very good illustration is right here in this picture of the cubic polynomial. One of the things that we use to find local minimum and maximum are called critical values or critical numbers. A point is a critical number if, I'll say a point C is a critical number if f prime of C equals 0 or f prime of C doesn't exist. If either of those happens at C, then C is a critical number. And also, another point to notice is that if a function has a local minimum or maximum at x is equal to C, then it is a critical number. Now that goes back to Fermat's theorem, if you think about it. Oftentimes, graphing is a great tool to identify minima and maxima of a function. So here is a simple function with a graph, and we have a set of points A, B, C, D, R, and S for x values, and we have to determine if they are maximums or minimums. So let's go ahead and look at the largest possible value of this graph, and that value is right here. And the smallest value that we can get for the function is right there. So that is the lowest y value that I can see, and that is the largest y value that I can see. And you have to note that A and S are endpoints. That's where the function ends. So the absolute maximum is at x is equal to S. The absolute minimum is at x is equal to R. But I kind of see a maximum over here, but it only happens about the value C. Maybe if I look at the tiny interval right there, then amongst all those y values, I have a maximum which happens at x is equal to C. So we call that a local maximum at x is equal to C. Using the same logic, we could draw a line on either side of R, and we will see that in that neighborhood, in that tiny interval about R, that value at x is equal to R is a minimum. So that absolute minimum is also a local minimum. Because, it falls in the domain of the function. And we move on to B. B has a dip here, and between two values close to B, that value that we observe at x is equal to B is small. So that is the lowest value on the interval around B. So that would be a local minimum also. And what about point D and A? Well, D is right here. It is not a peak, it is not a dip, and so it's neither a maximum nor a minimum. And if you look at A, it is the same argument, even though it is an endpoint. There are other values that are smaller or larger than what we see at x is equal to A, so neither a max nor a min at x is equal to A. A very, very important thing to note is the absolute max at x is equal to S. So even though we have an absolute max, this cannot be a local maximum. Why, you may ask? Because it is an endpoint. Keep in mind, for us to establish a local maximum, I need to draw an interval around the value that I'm looking at a local maximum for. So at S here, I could draw a line on this side to the left of S, but I can't draw one on the right because the function ends at the point S. So at x equals S, we have an absolute maximum, but we do not have a local maximum because it is an endpoint. Moving on to the next function, we want to find the smallest value that we can think of. Looks like that point at x is equal to A is smaller than that point at x is equal to S. So we have an absolute minimum at x is equal to A. It is smaller than every single value in the domain of the function. Could that be a local minimum? No. can't be because it is an endpoint. Now what about S? Is there an absolute minimum at S? Absolutely not, because we have the absolute minimum at x is equal to a. It's slightly lower than what we see at x is equal to s. But could there be a local minimum at x equals s? No. The reason being x equals s is an endpoint. So there is no local min or max at x equals s. What about the point x is equal to b? X is equal to b has a value defined, which is right over there. And that particular value on an interval about b is the largest value that we can think of. So that is the local maximum for b. So x is equal to b is a local maximum, because if we look at all the values for y in that interval, the largest value happens there. And we do the same for the point C. If I look at that interval, of all the values that I see, that particular point at x is equal to c doesn't correspond to a minimum, because there is a value smaller than what I see over there. In other words, the values there are less than what you see at x is equal to c. And clearly there is not a maximum, because that high value is not included. So x is equal to c is neither a local min or max. Then we move on to d. If we look at x is equal to d, on either side, that is the lowest value on either side of x is equal to d, that point right there is the smallest value for y. So x is equal to d is a local minimum. And lastly, we have a point right here, and that point at x is equal to r is an absolute maximum. Now, is it a local maximum also? Yes. If I draw an interval on either side of r, that particular value that we see at x is equal to r is larger than every single value of y on that interval. So it is also a local maximum. So a graph is of great help when we try to find maximum and minimum. So your calculator is very useful because we get to see the graph first, then we could use calculus to come up with a better mathematical approach. But to get an initial insight into the problem, it is always great to make use of your calculator. So here we have a function. The domain is 3 all the way up to infinity. If I rewrote this function, I can distribute that 3, 1 over 3, 3x, minus 2 over 3. The 3's would get cancelled. I have x minus 2 over 3. And you should be able to recognize what that function is. That is a linear function. The slope is 1. Y-intercept is negative 2/3. Let's graph this. And I'm going to adjust the window, put 3 all the way up to infinity. So I'm just going to leave it at 10. And I'm going to go for minus 2/3 as the minimum value. And that is the graph that I get. So on the domain of the function, we start at negative 2/3 here, but that's not part of the domain, and it keeps on going. So that would be the point 3. Corresponding value would be f(3). And it goes all the way up to infinity. Now, does it have an absolute maximum? So since the line is going toward infinity, there is no absolute maximum. Does it have a local maximum? It depends on the interval that we define. So I don't have a specific interval here, so we don't have a local maximum to look at. So, to quantify, because we don't have an interval that is specified. Is there a absolute minimum? So the absolute minimum is the smallest value. So the absolute minimum is at x is equal to 3. So f(3) would be equal to 3 minus 2/3. That would give me 7/3. So the absolute minimum is 3,7/3. Now, is that a local minimum? So there is no local minimum at x is equal to 3, because x is equal to 3 is an endpoint. Keep in mind, we can only quantify local extrema if I can draw an interval around the value on which you're trying to find the local extrema. So since 3 is an endpoint, I could look at an interval to the right of 3, but there is nothing to the left. So what do I mean by that? Let's see if it would help. Well, that didn't help. So I am going to put dotted lines up to 3 and solid lines, because that's where the function starts. So to the right of 3 I have an interval, I can form an interval, but to the left of 3 I cannot, so there is no local minimum at x is equal to 3. So here we have another function, which is f of x is equal to 2/x plus 1. The domain here, 1 is not included, all the way up to 5 is included. So let's go ahead and graph this. I'll have to adjust the window, obviously, because we are getting into fractions. So the y values, I'm just going to set it between 0 and 0.5. And that's the curve we are looking at. When x is 1, f of 1 would be 2 over 1 plus 1, which is 2 over 2, and we end up getting 1. So x is 1, and I have 1, but keep in mind, I am not including 1 because it's not part of the domain. And when x is 5, I have 2 over 5 plus 1, which is 2 over 6, and that would be 1 over 3. And that would give me 0.33, so perhaps I could put it over there. And it's a curve of that sort. So does this function have a local maximum or a minimum or absolute maximum? There is no absolute maximum. Because x is equal to 1 is not included in the domain. Is there an absolute minimum? The absolute minimum occurs at x is equal to 5. However, it is not a local minimum. Why is that? You can only form a local minimum around a particular point if you can have an interval, but there isn't such an interval, so we can't say that there would be a local minimum at x is equal to 5. A simplest way to look at it is because x is equal to 5 is an endpoint. So graphs are quite helpful in getting an insight into extreme values. Here we have an absolute value function. The domain is defined as -5 included, all the way up to +5. So let's go ahead and graph this. We could graph an absolute value by pressing math over to number 1 and 2 times x. I'm going to adjust the window from -5 to 5, and the y values are going to be positive because you can't plug in a negative number in an absolute value function and get a negative number, or for that matter any number. You can't get a negative number when we use an absolute value. So this is going to go from 0 to 10, call it 12, and let's graph, and that's what I would have. The endpoints are included. So that's at 5. That's at -5. And 0. When x is 0, it would be 0. And it is a v-shaped function with a sharp turn. So we can assess and find a maximum if there is one, just by looking at the curve. So now it's interesting here because the lowest value of all possible values, it's obvious, and that happens at x is equal to 0. So x is equal to 0 would correspond to the absolute minimum. Would it correspond to an absolute local minimum? Yes. If I picked a tiny interval about the point 0, the value that I observe at x is equal to 0 is the smallest of all values. So f of 0 is 0, and it is the lowest, so that is also the local minimum. Now, does it have an absolute maximum? Well, the largest value that we can think of is 10. So when I plug in f of 5, I get absolute value of 2 times 5, absolute value of 10, which is 10. When I plug in negative 5, I get absolute value of 2 times negative 5, which should be absolute value of negative 10. I still get 10. So naturally, a function can have two absolute maximums, or two or more. It could repeat. So here we have an absolute maximum, but are these absolute maximums also local maximums? No. And why is that? Because they are at endpoints. Keep in mind, if we have to find the local maximum or minimum, we need to have an interval about a point. So at 5, I can only form an interval, one-sided interval here on the left. And at negative 5, I can only form a one-sided interval to the right, because the function ends at negative 5 and at 5.